Hello students, I hope you all are doing good. So today we are going to discuss NCERT section 12.5 and 12.6 of chapter Atoms. This is the disclaimer. Let's start by looking at what you will be able to do after this lecture. Our focus is on atoms and we will be building up your understanding step by step. First, you will learn how Bohr's postulates and the Rydberg formula help us explain the line spectra of hydrogen. We will go through the math behind these ideas, but also talk about what the spectral series mean physically. Next, you will be able to comprehend de Broglie's wavelength wave-particle duality concept. This idea says that particle-like electrons can behave like waves, and this helps explain why only certain orbits are allowed in Bohr's model. You will see how the standing wave condition leads to quantized orbits and how this supports Bohr's second postulate. Let's see the index of topics that we are going to cover today. Firstly, we will discuss NCERT section 12.5, that is the line spectra of hydrogen atom. Next, we will look at NCERT section 12.6, that is de Broglie's explanation of Bohr's second postulate of quantization. De Broglie suggested that electrons behave like waves and only certain wavelengths fit perfectly around the nucleus, leading to quantized orbits. We will explore how this wave nature leads to quantization with some examples in the next section. Let's start by considering what happens when an electron in an atom moves from a higher energy level, which we will call Ni, to a lower energy level, Nf. Remember, Ni and Nf are just numbers that label the different allowed energy levels in the atom, and Nf is less than Ni. Now, according to Bohr's third postulate, whenever an electron jumps from a higher energy state Ni to a lower energy state Nf, the atom emits a photon. The frequency of photon is called nu if. Let's look at the energy involved. The energy of the emitted photon is exactly equal to the difference in energy between the two states, the higher energy ENI and the lower energy ENF. This means the atom loses energy as the electron drops down. Here is the key formula. H nu if is equal to H ENI minus ENF. In this equation, H is Planck's constant measured in joule seconds. Nu if is the frequency of the emitted photon in hertz, and ENI and ENF are the energies of the initial and final states in joules. Finally, notice that because Ni and Nf can only be certain whole numbers, the energy differences and therefore the frequency of light emitted are also specific values. This is why atoms emit light at distinct separate colors, not a continuous rainbow. This explains the line spectra we see in experiments with hydrogen and other elements. Let's start by looking at how we use the energy level equation for atoms. The equation 12.8 shown En equal to minus m e raised to power 4 upon 8n square h square epsilon naught square gives the energy of an electron in the nth orbit of a hydrogen atom. Here m is the electron mass in kilograms, e is the elementary charge in coulombs, n is the principal quantum number, just a positive integer, h is Planck's constant in joule seconds, and epsilon naught is the permittivity of free space in farads per meter. We will use this equation and substitute it into another equation 12.11 to see how energy changes when an electron moves between orbits. Now let's look at what happens when an electron jumps from one energy level to another. The equation here shows the energy difference between two levels, Ni initial and Nf that is final level. Notice that we subtract the energy of the final state from the initial state, which gives us energy of the photon emitted or absorbed. This energy is equal to h times nu if, where nu if is the frequency of the emitted photon. Okay, and the equation is h nu if equal to, so for initial energy of initial level, that is minus m e raised to power 4 upon 8 n I square h square epsilon naught minus energy of final energy state. Okay, that is minus m e raised to power 4 upon at 8 nf square h square epsilon naught square. Next, we simplify the equation by factoring out the constants. Now h nu if equals to m e raised to power 4 divided by 8 h square epsilon naught square times the difference between 1 over nf squared and minus 1 over ni squared. This shows the frequency of the emitted or absorbed photon depends only on the difference between the two energy levels. For example, if Ni is 3 and Nf is 2, you can plug in those numbers to find the frequency of the photon. Finally, let's relate frequency to wavelength using the equation nu equal to c upon lambda, where c is the speed of light in meters per second. Rearranging gives us c upon lambda if equals to same constant, that is m e raised to power 4 upon 8 h cube epsilon naught square. Okay, this constant and this constant times the difference in the inverse square of quantum numbers. This means wavelength of light emitted or absorbed depends on the energy difference between the two levels. Let's start by looking at this important formula for the wavelength of light emitted or absorbed when an atom moves between energy levels in a hydrogen atom. The equation shows 1 divided by lambda if, which is the reciprocal of the wavelength, equals a constant. What is the constant now? M e raised to power 4 upon 8 h cube epsilon naught square c, multiplied by the difference between 1 over nf squared and 1 over ni squared. Here ni is the initial energy level and nf is the final energy level. Now let's focus on the constant in this equation. The term in brackets, okay, which is m times e raised to power 4 divided by 8 times h cube epsilon naught square times c, is known as the Rydberg constant. This constant combines several fundamental physical constants and it is denoted as Rh. After substituting the values for all these constants, like the mass of electron, the charge of electron, Planck's constant, the permittivity of free space and the speed of light, we get a specific value for the Rydberg constant. Let's see what that value is. The Rydberg constant Rh is equal to 1.097 times 10 raised to power 7 per meter, or we can say meter inverse. This means that for hydrogen, every time we use this formula, we can plug in this value for Rh to find the wavelength of light emitted or absorbed during electron transitions. With this value, we can now write the Rydberg formula in much simpler form. Here is the simplified Rydberg formula: 1 divided by lambda if equals Rh times the difference between 1 over nf squared and 1 over ni squared. This boxed equation is the only one you will use most often to solve problems about hydrogen spectral lines. Finally, let's clarify that lambda if is the wavelength of the photon that is emitted when an electron transitions from a higher energy level to lower energy level. The greater the difference between Ni and Nf, the shorter the wavelength and the higher the energy of the photon. Let's start by looking at the spectral series of the hydrogen atom. This topic helps us understand why we see specific lines of color when we look at the light given off by hydrogen. These lines are not random. They tell us something important about how electrons behave inside the atoms. Now let's see how these lines are actually produced. Notice that these lines appear when electrons jump from a higher energy state to a lower energy state. When this happens, the atom releases energy in the form of photon, which is a particle of light. For example, if an electron falls from the third energy level to the second, it emits a photon with a specific amount of energy. And that's what creates a visible line in the spectrum. These lines are called emission lines. The term emission means the atom is giving off energy as light. Each emission line corresponds to a specific energy difference between two electron levels. So the pattern of lines acts like a fingerprint for each element. But what happens if we shine light on the atom? If a photon has just the right amount of energy, it can be absorbed by an electron, causing the electron to jump to a higher energy state. This process is called absorption, and it's the opposite of emission. When light with a continuous range of frequencies passes through a gas, the atoms in the gas absorb only certain specific frequencies. This creates a dark absorption lines in the spectrum, which are the exact frequencies that the atoms absorb. These absorption lines help scientists identify which elements are present in stars and other distant objects. So let's start by defining what a spectral series is. In a hydrogen atom, a spectral series is a group of emission lines. These are bright lines seen in the spectrum when the atom emits light. Now let's look at how these lines are formed. When an electron in a hydrogen atom drops from a higher energy level to a specific lower energy level, it releases energy in the form of light. The energy difference between these levels determine the color or wavelength of the light emitted. Notice that each transition produces a photon with a very specific wavelength. That's why we see sharp, distinct lines in the spectrum, rather than a continuous spread of colors. Each line tells us about a particular jump between energy levels. These series are named after the scientists who discovered them, like Balmer and Lyman. The pattern of these lines can be predicted using the Rydberg formula, which relates the wavelengths to the energy levels involved. The Balmer series is especially important because its lines appear in the visible part of the spectrum, the colors we can see with our eyes. Other series like the Lyman series are found in the ultraviolet region, which we can't see, while the Paschen, Brackett and Pfund series are in the infrared region. This shows that hydrogen emits light across a wide range of wavelengths, not just visible light. Let's look at the main spectral series of the hydrogen atom. Each series is named after the scientist who discovered it, and each one is linked to the electron transition between different energy levels. We will go through each series and see where it appears in the electromagnetic spectrum. First is the Lyman series. This series appears in the ultraviolet region of spectrum. It happens when an electron falls from a higher energy level like n equal to 2, 3, 4 and so on down to the lowest energy level, that is nf equal to 1. Next is the Balmer series, which is special because it's the only series visible to the human eye. Here electron drops from higher energy level, that is n initial for Balmer series is 3, 4, 5 and so on, and electron is dropped from higher energy level to lower energy level, that is n final is equal to 2 for the Balmer series. For example, when an electron falls from n equal to 3 to n equal to 2, it emits a photon of visible light. This is why we see distinct colors in hydrogen spectrum. Now we have Paschen series, which appears in the infrared region. In this case, electrons move from n equal to 4, 5, 6 and so on down to the n equal to 3. Okay, that means n final for Paschen series is 3. Since infrared light has longer wavelength than visible light, we can't see these lines with our eyes, but special detectors can pick them. The bracket series also lies in the infrared region. Here electron falls from n equal to 5, 6, 7 and so on from n equal to 5, 6, 7 and so on to down to n equal to 4. Notice how as the final energy levels increases, the emitted light shifts further into the infrared, meaning even longer wavelength and lower energy photons. Finally, the P-Fund series is another infrared series with electrons dropping from n equal to 6, 7, 8 and so on down to n equal to 5. To sum up, each series is defined by the final energy levels the electron lands on. Okay, so the n final for Paston series is 5, n final. And the region of the spectrum depends on how big the energy jump is. Now we are focusing on the Rydberg formula and how it helps us understand the spectral lines of hydrogen. The Rydberg formula is a key tool in atomic physics for predicting the wavelengths of light emitted by hydrogen atoms. Here you can see the image of the hydrogen line spectrum. Notice the distinct lines, each one represents light of a specific wavelength emitted when an electron in a hydrogen atom moves between energy levels. These lines are grouped into series and each series corresponds to electrons falling to a particular energy level. We will focus first on the Lyman series, which is shown here. So let's talk about Lyman series. In this series, electrons fall to the first energy level, which we call n final equals to 1. The Lyman series lines are all in the ultraviolet region of the spectrum, which means we can't see them with our eyes, but they are very important in understanding atomic structure. Here is the formula for the Lyman series. 1 divided by lambda I1 equals RH times 1 divided by 1 squared minus 1 upon Ni square, where Ni is 2, 3, 4 and so on. RH is the Rydberg constant, which has a value of about 1.097 times 10 to the power 7 per meter. Lambda I1 is the wavelength of the emitted light measured in meters. As Ni increases, the wavelength gets shorter, moving deeper into the ultraviolet region. For example, if Ni is 2, you get longest wavelength in the Lyman series. And as Ni goes to infinity, you approach the series limit. Now let's focus on the Balmer series, which is especially important because it includes all the visible lines in the hydrogen spectrum. In the Balmer series, the final energy level NF is 2. That means electrons are falling to the second energy level from higher levels. And that's what produces the visible light we can see. Here is the formula for Balmer series. 1 divided by lambda I2 equals to RH times 1 divided by 2 squared minus 1 divided by Ni squared, where Ni is 3, 4, 5 and so on. RH is the Rydberg's constant and lambda I2 is the wavelength of light emitted and Ni is the initial energy levels. Let's focus on the Paston series, where the final energy levels NF is 3. This means electrons are falling to the third energy level from higher energy levels. The Paston series lines are found in the infrared region of the spectrum, which is not visible to our eyes, but can be detected with special equipment. The Rydberg formula for the Paston series is written as 1 upon lambda I3 equals to RH times 1 upon 3 squared minus 1 upon Ni squared, where Ni is 4, 5, 6 and so on for the Paston series. Okay, here lambda I3 is the wavelength of the emitted light, RH is the Rydberg's constant and Ni is the initial energy level. As Ni increases, the wavelength gets shorter. Similarly, we can use the Rydberg's formula to find the wavelength for other spectral series, like by changing the value of NF. The key idea is that each series corresponds to electron dropping to a specific lower energy level. Let's start by looking at de Broglie's hypothesis, which is a key idea in modern physics about the nature of particles like electrons. De Broglie suggested that particles can behave like waves, not just like tiny balls. This idea helps us understand why electrons in atoms have only certain allowed orbits. Here we see a figure 12.8 showing a standing wave on a circular orbit. Notice how the wave fits perfectly around the circle, with 4 complete wavelengths fitting into the circumference. This is similar to how a guitar string can only vibrate at certain frequencies to make a clear note. Louis de Broglie argued that we can think of an electron in a circular orbit as both a particle and a wave. This means the electron's wave must fit exactly into the orbit, just like the standing wave in the diagram. If the wave doesn't fit, it cancels itself out, so only certain orbits are possible. This wave-particle duality is a big step in understanding atomic structure. Just like with waves on a string, only certain resonant frequencies will create standing waves. For electrons, this means only certain wavelengths and therefore certain energies are allowed. If the electron's wavelength doesn't match the orbit, it can't exist in that state. When you pluck a string, it tries to vibrate in many ways, but only the vibrations that fit the length of the string with nodes at the ends will last. The same idea applies to the electrons. Only the waves that fits perfectly around the orbit will survive. This is why atoms have discrete energy levels. Here figure 12.8 shows a standing wave pattern. Notice how the wave fits perfectly around the length of a string, creating distinct nodes and antinodes. This is similar to how electron can form standing waves around the nucleus in an atom. Let's examine how standing waves are formed. For a standing wave to exist, the total distance the wave travels down the string and back must be exactly one wavelength, two wavelength, or any whole number of wavelengths. This is called the resonant condition. If the wave doesn't meet this condition, it can't form a stable standing pattern. Notice what happens if wavelength doesn't fit the resonant condition. Waves with these wrong wavelengths will interfere with themselves when they reflect back, causing destructive interference. This means the peaks and the troughs of the wave cancel each other out, so no standing wave forms. This destructive interference quickly reduces the amplitude of those non-resonant waves to zero, effectively cancelling them out. Only the waves that meet the resonant condition survive. This is why in atoms only certain electron wavelengths and therefore certain energy levels are allowed. Now let's think about what makes an electron's orbit stable. For the electron to stay in a fixed orbit, its wave must fit perfectly around the circle. This is similar to how a guitar string only vibrates at certain frequencies to make a clear note. If the wave doesn't fit, the orbit won't be stable. Specifically, the electron's wave must form a stationary wave, also called a standing wave. A stationary wave is a wave that doesn't move along the orbit, but instead has fixed points called nodes. This means the electron's wave pattern repeats perfectly as it goes around the nucleus. This can only happen if the circumference of the orbit is an exact multiple of electron's wavelength. In other words, the length around the orbit must be equal to 1, 2, 3 or more full wavelengths. According to de Broglie, a stationary orbit is only possible if it contains an exact whole number of standing waves. That means the electron's wave must fit perfectly around the orbit with no gaps or overlaps. For an electron moving in the nth circular orbit, the total distance it travels in one complete revolution is the circumference of the orbit, which is 2 times pi times the radius, or we can say 2 pi Rn. Here Rn is the radius of the nth orbit, measured in meters. This formula gives us the path length the electron's wave must cover. So for an orbit to be allowed, the circumference must equals n times the wavelength, or we can say 2 pi Rn is equal to n lambda, where n is a whole number, 1, 2, 3 and so on, and lambda is the wavelength of the electron. This condition ensures that electron wave forms a standing wave around the nucleus. Mark it as 12.12 equation. So figure 12.8 illustrates a standing wave on a circular orbit for n equal to 4. That is, the formula here is 2 pi Rn equal to 4 lambda. Means 4 wavelengths are accommodating in the nth orbit of electron. Tells us that circumference the orbit, which is 2 times pi times the radius of the nth orbit, is equal to 4 times the wavelength of the electron. This is what allows a standing wave to form. If the circumference doesn't match a whole number of wavelengths, the wave would cancel itself out and the orbit won't be stable. Here lambda stands for the de Broglie wavelength of the electron, which describes the wave-like behavior of the electron as it moves in the nth orbit. Remember, the de Broglie wavelength depends on the electron's momentum, and only certain wavelengths and therefore certain orbits are allowed. Now let's recall from the chapter on the dual nature of radiation and matter that the wavelength lambda of a particle is given by lambda equal to h divided by p. Here h is the Planck's constant, which has a value of about 6.62 times 10 to the power minus 34 joule seconds, and p is the momentum of the electron, measured in kilogram meter per second. If the electron speed is much less than the speed of light, we can use the classical formula for momentum, which is mass times velocity. So the momentum p becomes m times vn, where m is the mass of electrons in kilograms and vn is the speed of electron in nth orbit measured in meter per second. Substituting this value of momentum into our earlier formula, we get lambda equals to h divided by m times vn, where vn is the speed of electron in the nth orbit. This equation shows us that the faster the electron moves, the shorter its wavelength will be. From equation 12.12, we have a relationship involving the circumference of the electron's orbit. This sets up the condition for standing waves, which is essential for understanding why only certain orbits are allowed for electrons. So we arrive at the equation 2 pi Rn equals n times h divided by mvn. This means that the circumference of the nth orbit, that is 2 pi times the radius, must be exactly n wavelengths long. In other words, only those orbits where the electron's wave fits perfectly are allowed. Now let's look at the key equation mvn equal to nh upon 2 pi, which is equal to nh upon 2 pi. Here m is the mass of the electron, vn is the speed of the electron in its nth orbit, rn is the radius of nth orbit, and n is a positive integer called a quantum number, and h here is Planck's constant. This equation is actually the same quantum condition that Bohr proposed for the angular momentum of the electron. Bohr suggested that electrons could only occupy orbits where their angular momentum is a whole number multiple of h divided by 2 pi. De Broglie's hypothesis gives us a physical reason for why angular momentum is quantized. It says that only certain orbits are allowed because the electron's wave must fit perfectly around the orbit, like a standing wave on a string. So, to sum up, the reason electrons have specific orbits and energy levels is because of their wave nature. The wave-like behavior of electrons means only certain orbits are possible, which leads to quantized energy states. Let's look at the limitations of the Bohr's model of atom. The Bohr model was a big step forward in understanding atomic structure, but it doesn't explain everything. We will go through its main limitations, especially when it comes to atoms beyond hydrogen. First, notice the Bohr model is only really accurate for hydrogenic atoms. These are atoms or ions that have just one electron orbiting the nucleus, like hydrogen itself. Let's see what this means in more detail. For example, the Bohr model works for hydrogen but also for ions like singly ionized helium, that is helium positive, and doubly ionized lithium, that is lithium 2 positive, because they have only one electron. In these cases, the electron moves around the nucleus in a way the Bohr model can predict. However, the Bohr model cannot be used for atoms with more than one electron, such as helium in its normal state. In these atoms, the interaction becomes much more complex, and the Bohr model prediction no longer match the experimental results. Scientists tried to extend the Bohr model to atoms with more than one electron, but these attempts were not successful. The model simply couldn't handle the extra complexity introduced by additional electrons. The main issue is that in multi-electron atoms, each electron feels forces not just from the nucleus, but also from all the other electrons. This makes the system much more complicated, and the simple Bohr model can't account for these interactions. To sum up, the Bohr model's equation only considers the force between the nucleus and a single electron, ignoring the force between the electrons themselves. This is why the model fails for atoms with more than one electron. Bohr model can't explain why certain frequencies in the hydrogen emission spectrum are more intense than others. The model predicts the position of spectral lines, but it doesn't tell us why some lines are brighter or dimmer. Let's explore this in more detail. Bohr's model does a good job at predicting the actual frequencies of light that hydrogen emits. For example, it can tell us exactly where the red or blue lines will appear in the spectrum. This was a major success for the model and matched experimental data very well. However, if we look at the real hydrogen spectrum, we see that not all visible lines are equally bright. Some frequencies stand out with strong intensity, while others are much fainter. This means that amount of light or intensity varies from one spectral lines to another. Experiments show that this difference in intensity is because some electron transition between energy levels are more likely to happen than others. In other words, certain jumps between energy levels are favored, so they produce stronger lines with stronger intensity. The Bohr model doesn't explain why these probabilities are different. To sum up, the Bohr model can't account for the variation in transition probabilities or the observed difference in line intensities. This limitation led scientists to develop more advanced models like quantum mechanics, which can explain these details. Now let's summarize the topics that we have discussed today. Let's start by looking at the line spectra of the hydrogen atom. So Bohr's third postulate explained that the spectral lines of hydrogen are due to electron jumping between different energy levels in an atom. When an electron moves from a higher energy state to a lower energy state, it emits light at a specific wavelength. Next, notice that energy of the photon emitted during this transition is equal to the difference in energy between the two states. In plain terms, photon energy E equals to h times frequency. So E equal to h nu IF. And that's also equal to the difference between the initial and final energy levels. That is ENI minus ENF. Here h is Planck's constant measured in joule seconds and nu IF is the frequency in hertz. Finally, about the Rydberg's formula, let us calculate the exact wavelengths of the spectral lines using quantum numbers, which are just whole numbers that label the energy levels. By plugging in different values for the initial and final quantum numbers, we can predict the wavelengths we see in hydrogen spectrum. Let's look at de Broglie hypothesis, which is a key idea in modern physics. This hypothesis connects the behavior of matter like electrons to the concept of waves. We will see how this idea explains why electrons behave the way they do in atoms. De Broglie proposed that all matter, not just light, has both particle and wave properties. He gave us a formula for the wavelength of a particle, lambda equals h divided by m times v, where lambda is the wavelength, h is Planck's constant, m is the mass, and v is the velocity of electron. De Broglie suggested that electrons in stable orbits must form standing waves around the nucleus. A standing wave is a wave that fits perfectly into the space, like a guitar string vibrating at certain frequencies. For a standing wave to form, the circumference of the electron orbit must be an exact multiple of its wavelength. In other words, 2 times pi times the radius of orbit equals to n times lambda, where n is an integer 1, 2, 3 and so on. This means only certain orbits are allowed, which matches that Bohr found experimentally. This standing wave condition means that only orbits where a whole number of wavelengths fit exactly around the nucleus are possible. If the wavelength doesn't fit perfectly, the wave cancels itself out and the electron can't stay in that orbit. De Broglie's idea leads directly to the Bohr's rule for angular momentum, L equals to n times h divided by 2 pi, where L is angular momentum, n is an integer, h is Planck's constant. This formula shows that angular momentum is quantized, not continuous, which was a mystery before de Broglie's explanation. In summary, the de Broglie's hypothesis gave a physical reason for Bohr's second postulate, which had previously just been assumed. Now let's see some practice questions based on today's topic. Let's start by looking at the de Broglie wavelength formula for matter waves. This formula tells us how particles like electrons can behave like waves. Okay, now let's see the second question. According to de Broglie, how many wavelengths must fits into the circumference of the orbit for a stable electron orbit? Next, what happens when an electron moves from a higher energy level like n equal to 3 down to lower one like n equal to 2 in a hydrogen atom? Does it emit energy or absorb energy? So this is all about today's lecture. I hope you enjoyed the session. Thank you for your attention.